Well, hello everybody. Welcome to the last section of this class, Chapter 11, Part 2, Simple Linear Regression. So we're going to just go over the second part of Chapter 11 today. Last week we talked about correlation, which was the first part of Chapter 11, and regression just builds on correlation. And what you'll see today is that correlation, as we talked about, is about how two variables are related or associated. We talked about the strength of the relationship and the direction of the relationship between two variables. Whereas with regression, we're going to start to talk about prediction, which is the next step, which you'll see today. So regression predicts, and correlation describes relationships and associations. Simple linear regression, which is what we'll learn today, predicts an individual's score on the dependent variable based on their score on the independent variable, and in this case we're only talking about one independent variable and one dependent variable. There are more complex versions of regression, multiple regression, where you've got more than one independent variable, but in this case we're going to predict an individual's score on the dependent variable based on their score on the independent variable. When you run a simple linear regression, you're going to be able to calculate a straight line that describes the data. And so in simple linear regression, we're actually trying to find the best fitting linear equation that fits the given data points. If you recall, when we talked about correlation and we graphed the correlation with the scatter plot, it's very unlikely in psychology research or any behavioral research that you'll find data that are perfectly linear related, like a correlation of 1 or -1. So we have to find the best fitting line through data points that are a little bit messy. So for linear regression, we have a formula. This is y with this little symbol over the top. We call it y hat, or that's your predicted y-score, and that's based on this equation, a plus bx. This is the equation for a line, where a is your y-intercept, b is your slope, and x is the person's score on the independent variable. So this looks very much like the equation that you used probably in algebra, y equals mx plus b. It's the same formula, it's just that in this case, instead of m for slope, b is our slope, bx. Y is equal to mx plus b, and a is our y-intercept, instead of it being symbolized by the letter b when you probably did this perhaps in high school. So here's our formula for a line. We've got our y-intercept, and that's the predicted value of y when x is 0. Where does the line cross the y-axis? And b is slope. That's the amount of change in y predicted for an increase of 1 on x, whatever the independent variable is. So there's your slope, there's your y-intercept, this is your independent variable x, you plug it in, and it gives you a prediction for y. So here's an equation for a line. Here's our formula. Y hat is equal to 5 plus 2x. 5 is your y-intercept, meaning here's our y-axis. When x is 0, right, x is our horizontal axis. When x is 0, y is 5. And you can see that right there. And that makes sense because here if you put in a 0 for x, then this becomes 0. 2 times 0 is 0. And you end up with y equaling 5. So when x is 0, y is 5. And then you can put any number in here for x and calculate the prediction for y. So if we put a 1 in for x, so when x is 1 over here, 2 times 1 is 2, plus 5 is 7. So when x is 1, y is 7. And then when x is 5, let's say, 2 times 5 is 10, plus 5 is 15. So when x is 5, y is 15. And you can do this and create a line. Here it is. Now typically, our data isn't perfect like this. This is a perfect correlation between these two variables, right? There's no variability. All the dots fall on this line. When we are creating regression lines in psychology, this is our data on number of absences and exam grade. It's not so perfect. The data looks a little bit messy. And when you run your regression analysis, which we'll do in our next SPSS lecture, what you get, or what the regression does, is it calculates the line of best fit, meaning what's the equation for the line that goes through your data points with the least amount of error, that's the kind of closest to all the data points and creates the least amount of error. So this would be the line of best fit through this set of data. And how it works, once you run your analysis, you get something that looks like this. A couple of things that are important for us. I have here the effect size. So the effect size in this case is what we call R squared. Just like we used in ANOVA, we used R squared, which is the percent of variability in the dependent variable that's accounted for by the independent variable. So you can come over here to R squared, and it's 0.72 or 72%, 72.4% of the variability in exam grade, that's our dependent variable, can be accounted for by absences. Absences is our independent variable. So when we're looking at the variability in people's exam grades, right? Some people got 100%, someone got a 50%. There's a lot of variability. 72% of that variability can be accounted for by how many classes they missed. That means that there's still quite a bit of variability unaccounted for, right? It's not that the whole story is number of absences. If that was it, if all you needed to know was number of absences in order to find someone's exam grade, then these lines should fall in a perfect line. That it would be a perfect correlation because nothing else impacts exam score but number of absences. In this case, it's not that case. That number of absences tells us something. It gives us some way to predict that as people missed less classes, they have higher grades, and as people missed more classes, their grades are lower, but it's not a perfect correlation. So that's what this R squared in your model summary gives you. It's the effect size. And then we skip this whole ANOVA table, and all we need to do is go down to coefficients, and you want this column that says B, gives you a constant, 94.362. This is your y-intercept. And then under here, absences, this is your slope. Okay, so these are the only two numbers we need for our regression analysis, and we can put those in a line, in an equation for a line. So the equation for the line is A, which is the y-intercept, plus B, which is the slope, times x. So the y-intercept, 94.33, is coming right from here. 94.33 gives you your y-intercept, plus a slope of negative 5.39. And it's right here, negative 5.39. A negative slope means that for every unit you go up on the x-axis, so in this case, every time you go up for one absence, from 0 to 1, or 1 to 2, or 2 to 3, you're going down 5.39 points in this case, exam grade. And if this was positive, that would mean that for every one you go up here in on the x-axis, you go up on the y variable as well. But this is a negative correlation, 94.33, which is where this line crosses the y-axis. So when x is 0, if you missed 0 classes, our best prediction of your statistics exam grade would be 94.33. And as you go down, or as you go up every point on x for 1, as x becomes 1 or 2 or 3 or 4, you fill that into the equation to get the person's best estimate of their score. Now, will the estimate be perfect? No. As you can see, all these dots don't all fall on this line, and nobody's, necessarily will fall exactly on this line, but this gives us our best prediction. So we could say, if somebody missed 10 classes, I could plug 10 into this equation and get, well, this is my best estimate of how I think this student will do on the final exam grade. It won't be a perfect estimate, but it'll be the best we can do, which is the idea of standard error of the estimate. This is the typical distance between the regression line and the actual data points. So here's our best fit regression line, and here are our data points. And the idea is how much error there is has to do with how much variability or how much distance there is between these data points and the regression line that we created. So if you look here, here are two sets of data points, the same regression line going through them. In which case do you think standard error is smaller? Or which one makes the stronger prediction? Which line is a better, more accurate prediction? Hopefully you're going to see that it's this A. This has the better prediction because the data points are more closely clustered around this line. There's less error. There's less standard error of the estimate. Whereas with this line, it's still our best fit regression line, but you can see there's a lot more distance between the data points and the line, which means there's more error in our prediction. When we predict somebody in terms of 6 on whatever this x variable is, and this is their what we predict for y, about 3, you can see that that's our best guess, but there may be quite a bit of variability, quite a bit of error in that estimate. Whereas here, when we predict, again, at 6 on x, 3 on our y variable, you can see that there's going to be a little bit less error. It's a bit of a better prediction because these dots, these data points, are more closely clustered around the line. Okay, that's it for this lecture, and then I'll show you how to run the regression analysis when we go into your next lecture on SPSS. Thank you.